Welcome back. We're going to talk about the system design or the online wallet, whether it can be a PayPal or a bank or a Venmo, anything where you have money and you want to be able to transfer those money to a different account. This is a very popular system design equation just because you can implement it in so many different ways. And in this video, we're going to talk about 4 different implementations, starting from a small scale, ending with a large scale system design. We'll talk about different concepts like distributed transactions. We'll talk about two-phase commits, compensating transactions, try, confirm, cancel, Saga pattern. We'll talk about event sourcing, distributed event sourcing. All these different design concepts can be used to implement our system in one way or the other. So with that, let's go to the video. Let's start with basics. We need to be able to transfer money between two accounts. The file-level data structure that we need is simple map. We need an account ID and a current balance for a specific user. If we have that, we should be able to subtract balance from one account and add it to another account. These are two actions that we would need to perform. The problem here is that we need to make sure that both of these operations are in the same transaction. So if we subtract the balance from one account, we need to be sure that we're going to add to another one. And if we can't, then the transaction has to be rolled back and the balance returned back to their sender. The most trivial way to implement it is just to make sure that we use a relational database and we perform these two actions in the same transaction. So if our user base is small and we don't need any distributed systems, we can just use a single database with master-slave replication. And what we need to do is just make sure that we implement two operations in the same transaction. It can be easily done using any of the relational databases. But now the question is, what if we have a lot of users and one database is not enough to maintain the state of all the users? Or perhaps we have multiple geographies where we need to serve our users. Or it can be that amount of transaction is so high that a single database just can't handle it and we somehow need to shard it or partition the data. Now, if we simply shard the data, we'll have multiple Postgres databases. And as we do a money transfer, the sender and receiver might exist on different Postgres shards. So we would have two independent transactions performed on different databases. And this is where the challenge comes. What if one transaction succeeds and the other one failed? The first thing that comes to mind is to implement a two-phase commit transaction. This is a functionality that is very native to the SQL or relational databases and can be easily implemented. So as you can see on this diagram, the way it's done is it uses a notion of a coordinator. So our wallet service would be a coordinator of a transaction. So as we want to transfer balance from database A to database C, for instance, we would need to first lock both databases rows that participate in this transaction. Then we would write data to both of these databases and then execute two stages, prepare and commit. So on the prepare stage, the coordinator would make sure that the resources are available, the transaction can be executed, and everything is fine. And on the second phase, we would commit transactions to both databases independently, provided that we have a coordinator that in case one of the transaction fails on any of the databases, the other transaction would be rolled back and the whole transaction would be rolled back. So this way we relied on the wallet service and its role of a coordinator and making sure that if one transaction on the database fail, the other one would be rolled back and the balance would be recovered. So either both transactions succeed or both transactions fail. There are only two possible outcomes. This approach was popular back in the day, but it has a lot of disadvantages. The first one is performance. The way two-phase commit work is by locking rows for a very long time. So as you can see on this diagram, we lock in the very beginning both rows in the database and to keep them locked until the transaction either succeeds or it fails. So if one of the databases has network delays or it's overloaded, then the other database would be lagged for the duration of the whole transaction. Now I imagine you have tens of thousands of these transactions per second, and one of the databases has network issues. Then all the transactions that involve this database with network issues would stall, and all the databases that are part of those transactions would just have all the rows locked, or a lot of rows would be locked, and the performance would degrade dramatically. and spread across the whole database systems, across all the shards and the whole persistence layer. The second problem is the reliability of the coordinator. Since coordinator is a single point of failure, if the wallet service that acts as a coordinator in a two-phase commit transaction fails, then we don't know about the status of the transaction and we might end up with the partial update on the database. If the coordinator crashes at the commit phase after one of the transactions succeeds, then the other transaction might just never succeed and we end up with the partial state. So the way to handle this is just for coordinator to keep an internal state of the distributed transaction. So every single time coordinator moves from the stage 1 to stage 2, it would update its internal database in the wallet service, maintaining the statuses of the prepare stage and commit stage. And as those stages succeed or fail, it would update them. This way, if one of the transactions succeeds and then coordinator fails before the other transaction succeeds in the commit phase, we would end up with the partial state, and that state would be stored in the internal database of the coordinator and then can be monitored and recovered by the external service or the wallet service itself once it gets online. Now we've identified two major issues with two-phase commit transactions. The first one is performance because of the very long locks that span across multiple databases. And the second one is single point of failure of the coordinator that coordinates the transaction. So what's the alternative? And the alternative is to split that multi-database coordination, have local transactions, and introduce a notion of compensating transactions that would be executed in case local transactions on the database fail. So the good example of it is try, confirm, cancel. As you can see on the screen, it consists of two different phases. The first one is try, and the second one is either confirm or cancel. So on the try, we subtract balance from database A, and on confirm, we add a balance to database D. So these are two different transactions, independent from each other. But in case the confirm fails, we execute a compensating transaction, cancel, where we add the balance back to the database A. This way, we either succeed or fail, but confirm and cancel executed in the different transactions. The main benefit of this approach is that we don't have those cross-database locks anymore. We only have local locks in the database. So as you can see here on the first phase, we only lock one database A to subtract the balance. The database C in this case does nothing, it just waits. Once the subtraction is done, we go to the second phase, which is confirm stage. And as you can see on this diagram, is that on the confirm stage, we add balance to the database C and only lock the row in database C while updating the balance. And if this transaction is successful, we confirm that the whole distributed transaction was successful. If this transaction fails, then we proceed to the cancel stage. And on the cancel stage, as you can see, we execute the compensating transaction, which means we take this balance that we subtracted from the database A and we put it back in. This way, they only maintain those local locks on the databases and don't have cross-database communication. We still need a coordinator, and in our case, the coordinator is a wallet service still, and we will still need to maintain the state of the try, confirm, cancel. Because if the coordinator fails, we still have the same issue that we might end up as a partial state. So we'll still have that monitoring in place of the database for the partial state. But the benefit is that we fix the performance. We don't have any cross-database locks, and we execute small local transactions where the coordinator manages the state of the overall transaction. What's important to know here is that subtraction has to happen first, because if we end up with a partial state, we want to add balance elsewhere without subtracting it first. So in our case, we subtract the balance first, and if the transaction fails, we just put it back in. The order is important here, so we cannot add money first and then subtract. It has to be subtracted first and then added to a different account. This approach allows us to scale without sacrificing the performance. The most generic concept of try, confirm, cancel is Saga pattern. This is the pattern for distributed transactions that is often used in the microservice architecture, where instead of just heading two transactions, like in our case, Saga pattern can support multiple transactions across different microservices and databases. It's implemented in a very similar way, where you would have a coordinator that would maintain a state of all the distributed transactions. That coordinator would issue commands to different microservices and execute local transactions across microservices. As you can see on the screen, this is an example of the Saga flow, where it has multiple operations like create order, process payment, update inventory. All these actions happen locally in the microservices, but there is a overarching distributed transaction that is managed by the Saga flow. So in case a flow fails at some step, whether it's process payment or update inventory, the Saga execution coordinator would maintain a state in the database about every single transaction start and end. And in case the transaction in the middle or in the end fails, it would run a set of operations to roll back the state. So for a developer to work with Saga distributed transactions, one would need to write a set of actions for a transaction and then a set of rollback actions to do to roll back a transaction in case it fails at some point. All these approaches we've discussed for distributed transactions work to consistently transfer money from one account to the other one. But what they do not do is provide some sort of history or ability to recreate the history from scratch to the specific point in time. When we work with banks and money, we need to be able to reproduce the state to a specific point in time or reconcile a set of transactions for a specific period of time. So we can't really do it with the way we implement in this way. So to do that, we need the history database, some sort of ledger that would maintain all the transactions and be able to recover or recreate them from the scratch. One of the ways to implement it is to use event sourcing. Event sourcing allows us to maintain a set of events that happen to our database and change the state of the database. This way, if we have them, we can recreate the state of the database and all the accounts across the board at the specific time by just replaying those events from a specific point in time. This way is very popular and a really good fit for us when we want to maintain the state of all the account balances and make sure we can roll back the state or take a look at the specific point of time. There are a lot of challenges implementing digital wallet using event sourcing because first, it's by nature is synchronous. So we need to add a lot of different functionality and features to make sure that the state is consistent, to make sure that the state can be reproducible. I talk about it in details in my system design course. So if you want to learn more about it, go to my website and also check out my advanced system design course, where I covered the event sourcing for the digital wallet, as well as a lot of other deep dive concepts for the system design. But on this note, this is it for the video. I hope you found it useful. If you liked it, make sure to subscribe, and I'll see you in the next one. Bye.